So welcome to this session on how to run an ARM school program innovation day. And I'll take everybody through all the different elements of what makes up an innovation day, what the concept is, all of the different things you need to consider when setting it up and running it, because there's lots and lots and lots of things to think about, and it's more complicated than what you might presume when getting involved. So the agenda is we'll run through what the innovation concept is. We'll look specifically at the oil spill cleaner upper challenge, which is one of my personal favorite of the challenges that we do. And we'll look at two different elements of this: so preparing for the day in terms of the organisers, so obviously the people running the day, and then what the schools and learners, parents, teachers, that sort of thing need to think about, and the information that you need to tell them to make sure that the session runs smoothly. And you can see there on the right, there's a picture of one of the previous sessions that we did with a bunch of schools in the UK, and this was the same task that you guys will be doing, called the oil spill cleaner upper. And you can see there's a body of water which they test these on, and the students there are also taking turns with their robot projects, which we'll see in just a minute.
And I just briefly say, if possible, we'll field questions at the end of the session so that we can have the whole training session as one piece. Thank you.
So let's spend a bit of time thinking about what the Innovation Day concept is. So effectively, it's a competition, obviously, and we want students to express their ideas and work to create a solution to a problem, and that's a key part of this. And it's a full day project-based learning competition. So there's different elements there. They have a project which gives them a brief which they need to create a solution for, and they're competing in doing so. Now the competition bit is not like a typical competition. They are judged on things like collaboration, communication, the quality of the innovation that they demonstrate, and also to what extent they meet the success criteria. So it's not sort of it's a race to the finish. It's all about the quality of the product and the extent to which they innovate, and that's a really, really important thing to remember in this. It's slightly different to like a normal style of competition. Now, this does take up a full day. It's quite a long activity because there's lots of little bits that go along with it. There's the design section, there's the building section, and then the programming, and all of this sort of stuff happens all in tandem, and the students need to iterate on it several times throughout the course of the day. So that's a really important part of this, because this is not just a computer science challenge. This is also a physical computing challenge, so an engineering challenge, if you will. And some of the more tricky bits of this project is in the building, which we'll touch up on a little bit later on, because these are the areas that you need to consider when supporting learners. So what does it involve? We typically use teams of 4. So we usually have sort of 2 boys, 2 girls in each team, and each of them have a microbit. Now a V2 is preferable, being the latest of the microbits, but this project can be done with a V1 if you need to. All of these projects are contextualized to one of the global goals, and again we'll cover that in a bit more detail later on, but just know that it's all about solving a real world tangible problem. The students throughout the course of the day have to build and program an artifact. Now this is sort of a technical education term, which is they have to demonstrate their skills and knowledge of engineering principles and computational concepts through this artifact. And so each group will build something slightly different, and that's fine. You know, there's no wrong way to do this, and each project will be slightly different, and how they approach it will be slightly different. And that's all part of this, is that the students can differentiate from each other depending on the extent to which they apply thinking, critical thinking, problem solving, and resilience as much as anything else as well, because this does take quite a lot of thinking, especially with students that may not have used electronics before, or have not used robotics elements or programmed them using a microbit. The competition element, which is a big factor in all of this, has a marking rubric, and there are points associated with each of these sections, which is provided as part of the resources. So hopefully you've had a chance to see that. And so towards the end of the day, you need some judges that can go around and score the teams, and it's out of 5 for each category, and there's a description of each category, and that gives you some sort of a data-driven way of judging the groups, and that gives you sort of a point score to determine who the winners are. And some of these elements you can just do within sort of an hour towards the end of the day, and other bits like the the innovation of the product, you can tell from the design elements. But things like the communication and collaboration, that's something you need to be observing throughout the course of the day and seeing which teams can are effectively talking to each other and working professionally and demonstrating that gracious professionalism, which is a core part of this pedagogical style. As part of the day, it's not just building the product and programming the product. They also have to present their product and come up with a brand. They have to productize this whole thing. So they need like a logo, a name. They need to be able to explain to the judges within 2 minutes what their product does and how they've innovated. How have they solved the problem? This entire challenge revolves around the success criteria that we set them, and they need to be able to explain how they've met that in a short, concise, professional manner. And Dragon's Den is it's a TV show over in the UK and the US where you basically get 2 minutes in front of a bank of judges to present your solution, and then they can ask you questions, and that feeds into the to the judging as well. As I mentioned, the global goals is the context, and we'll interrogate that a little bit further on, but that's a really interesting set of problems. You haven't come across those before. And because this is a competition, obviously it's good to have prizes for this as well. And it's good to have them sort of educationally based. So usually we give away microbit based accessories, because the microbits that we provide for the day, we let the students keep typically. And so you can get a load of additional peripherals, control boards, other stuff, just so that when they take the stuff home after having created this artifact, they can do more stuff with it. So that's the sort of the Innovation Day concept in a nutshell, and we'll go through that in a bit more detail. So at a very high level, these are the sorts of things that you need to consider for the day. So some obvious stuff like food and drink, making sure that students bring packed lunches, and you're catering for things like allergies and the like, so that's something to consider. Refreshments as well. These tend to be quite very active days, so making sure that students and the teachers are involved have access to coffee and water and that sort of thing. Some more sort of pragmatic logistical things like where the venue is. Does it have sufficient parking? Do you have risk assessments for the day? Because certainly in the UK, there's a culture around if everything has to be risk assessed. There's a legal element to this, and you have to make sure that you have the requisite documents in order to make sure that the risk has been assessed and that students are safe, and that schools are confident in the fact that this stuff has been thought about and any risks have been mitigated sufficiently. Also, if you plan to film the day, it's usually sensible to get some sort of media consent. We typically film our events, and unless schools have this sort of stuff already sorted out, which many do, it's good to get either parental consent or something from the school saying that this has been agreed in advance, so that you can use it for public relations stuff and marketing and all those sorts of good stuff. Because this, when you run these days, it's a really visceral, exciting, energy-filled day. The kids really get a lot out of it, and it's good to capture that sort of stuff and use it to share, how these experiences are really valuable for learners. It's also a good opportunity to think about how you can engage the teachers, because whilst the students are working away on this, the teachers are there to sort of supervise the students, but also you can put on some sort of training, or you can put on other activities if there's third parties that you work with that provide things for schools. That might be an opportunity to do that sort of thing. One of the most important factors is the hardware. And this is something you need to spend a bit of time thinking about, because this all needs preparing in advance. For example, each team of 4 needs a laptop with internet access, and it needs to be able to access the MakeCode environment and also GitHub, because some of the peripherals that we use for this activity are based on GitHub, and so that needs to be whitelisted. So it is totally worth taking a set of this equipment and going to the venue where you will be holding this event and making sure that you can actually go from end to end with the tool chain to make sure that you can first of all access the MakeCode website, create a hex file, download it to the microbit, over Wi-Fi, etc., and all that works. Now, it seems like an obvious thing that will just work, but it's worth checking all of that, because we've had this in the past where firewalls have blocked access to GitHub, for example, and that can cause a bit of a problem on the day, and it can ruin the flow, and can, if you don't find this until the students are tripping over it, it's a bit of a problem. So do check that it all works beforehand. And it's a good idea as well to let students bring smartphones, not just because it's all ARM technology, which is obviously an interesting thing from our perspective, but also because when they're creating their media for the day, for example, creating their branding, they may have like Google accounts, for example. They may want to set up a website as part of their marketing. They may want to use online graphics tools to create their branding and that sort of stuff. They may want to create like TikToks or YouTube Shorts, that sort of thing. All of which will help their marketing and branding score. So encourage them to do that sort of stuff, and it adds an extra sort of fun social element to it as well. So let's dive a little bit further into the sort of structure and pedagogy of the day. So the project itself uses the ARM School's program schema, which is effectively those headings you can see on the slide there, where we first of all set out what the problem is, and we'll go into exactly what that is for this problem in just a minute. But it's effectively you're cleaning up an oil spill using a autonomous boat drone. So that's the sort of the context, and cleaning up oil spills is virtuous, and we don't want oil destroying habitats in the environment. And then in order to do that, we then lay out the success criteria, which is purposely designed to be a little bit open-ended, and we'll look at what that means in just a second as well. But that's essentially what they have to keep referring back to solve. And if they aren't solving it, then that's the teacher's job there, is to keep referring them back to that success criteria. We also encourage students to not use the scaffolded support material, but it's effectively like cheat sheets, if you think of it like that, where they're sort of partially worked solutions to some of the coding problems that can, if you've got a group that are really struggling, it's a good idea to give them some support just so they don't get stuck and then become disengaged, and then they can't progress. So you can do that just by using open questioning, which is relatively straightforward. Like, why doesn't this work? Have you thought through this? Talk me through this algorithm. Why is that piece of hardware not working, etc., etc. So you can do an awful lot just by using a questioning tool. But if you need to give them a partial solution, you can as well. And we'll look at an example of that a little bit as well. For students that complete this really quickly, because obviously there is a spread of ability in these groups, there are also stretch tasks, which are additional success criteria, which are still based on the same theme as the project, but just add on additional difficulty and complexity that they need to think about. And then at the very end, there's also the final thoughts, which is like a sort of a reflection on why we're doing this and why it's important to solve these problems. So that's the sort of the big picture of the schema and how the project is structured. And here's a little bit about the criteria itself. So again, teams of 4, they have to make sure they design the project. Now this is really important, and we provide a design sheet. You've probably seen this in the material that we provided, it's good to insist that they fill that in and design the product before they start building it. And it's super important, because first of all, that's one of the judging criteria. So to what extent does their design is it successful, and also to what extent does their product look like their design? That's the 2 elements that they need to consider. Most students just want to jump straight into the build, but there are various things they need to think about as part of that, and some of that is prompted in the design sheet. And also that's where they capture their marketing and that sort of stuff. It's a good idea to improve iteratively as well. So when they test this stuff repeatedly, for example, if their boat starts to sink, they need to fix that. When they first program the algorithm to mop up the oil spill, if it doesn't do what they're expecting it to do, obviously they have to go back and fix it. And that's a really important part of this, is it's never going to be perfect straight away. And that classic mentality of fail early, fail often. So don't let them be discouraged by not getting it right first time. And also collaboration. It's really important for the students to work as a team, because there are lots of different things that they need to pull together to make this project successful, and prompt them to do so. Your job when you're delivering this is not to give them the solution, it's to facilitate their success. It's to facilitate their learning and their progression through the challenge. So keep referring them back to the success criteria or the stretch tasks should they get to that point, and encourage them to work with each other. So global goals. If you've not come across these before, which I imagine if you're at ARM, then you will have done. This is a set of 17 global problems that impact us all, and there's a series of sub problems underneath them, which all companies that sign up to these pledges seek to address through their business and through their practices. And the one that we're going to focus on today is the life below water. And this is the sort of the top level context of the problem. We're trying to reduce marine pollution, and this context is the oil spill. So this is the setting the scene bits. This is the slide you'd actually show the students on the day, and it's worth spending a little bit of time just explaining to students what this is, because, for example, they may not have heard the terms algorithm, they may not have come across what a drone is. So it's worth spending a bit of time reading through this and explaining to them, what these terms actually mean, and especially around the bit about the drone and it being autonomous, insofar as that it should just be press a button and off it goes, and it goes and does what you want it to do without any other encouragement. You're not controlling it; it's not remote control, and they have to do that programmatically by writing an algorithm. So that is, it's important to labour that fact, and you can use visuals for this as well. And there are videos online if you want to go a little bit further and be a little bit more visceral. But essentially, it's yes, explaining what the context is and why they're doing this. And it's also useful to speak through this in terms of why would we use a boat drone rather than just doing it manually. What's the benefit of using a boat drone? And it's all about scale. You could set 10,000 of these things out into the wild and it could clean up an oil spill super fast, really efficiently, rather than people doing it. So let's move on to the success criteria. So this bit is super important to make sure the students understand what they're doing, and as you can see, some of the bits are sort of pulled out, the key words that they need to try and meet. And this isn't like a didactic list of, it's like a checklist. These are just sort of broad concepts that they need to try and make sure that their solution addresses, and they are relatively open-ended. And again, part of the problem with this is that it's to what extent that they can interpret these success criteria and solve them using the technology and the resources that they have to hand. So first of all, it needs to float. That's kind of an important one. We don't want microbits at the bottom of the paddling pool, because they'll stop working, obviously. And it needs to start with the press of a button. So that's the first key sort of prompt, really, for the learners in terms of how do you start to make this work. So they need to be able to press a button, which the microbit obviously has several of that they can play with, and then it has to be able to autonomously navigate over an area. So the oil obviously will be moving about, or it would be if this were a real project, and it has to be able to navigate over a given area to mop it up. Now, in the context of this problem, is the boat drones will be dragging a sheet of smart material. Now, this is a real product, and it soaks up oil, and then it can be wrung out and then reused to soak up more oil. So, and that's what the boat drone does. It'll be sort of following a pattern up and down to mop up this oil spill. And the idea is that you release a whole fleet of these and then go and do that. But the autonomous bit is really important. And I'm sure you're already thinking straight away, there's like, how do you deal with like the ambient sea conditions? How do you stop them from being blown off course? And these are all additional things that the students need to either discover or solve as they're working on this project. And that's also some of the stretch tasks as well. So that's the success criteria, and you can see there's already lots and lots of sub problems within these that students need to be able to think about and address and design out. But on the very, very simplest level, if they can get the boat drone to kind of go up and down in a sensible order, that's a great first step, and that's is partially successful, and that should be celebrated. But the more students think about this and the more they test it, the problem just becomes more complex, and they need to start addressing those as they work through it. So let's look at one of the other pedagogical tools as part of this. Now, they have to fill in this table as part of their design sheet, and it's a really important teaching tool, this idea of input, process, output, and it allows you to sort of systematize or design a system which allows them to think about what are the inputs to the system, how is that input processed, and what are the commands that sit underneath that, and then what is the output. So as you can see from this example, in this very, very simple sense, they press a button, there will be an algorithm, which could, for example, be a function, which will control the motors on the artifact to go forward, turn 90 degrees twice, go backwards, and go, and it'll basically follow a route over the given oil spill, and then they have to work out how to make that work with the servo controls. This is obviously just an example, and this is the sort of thing you could speak to the students about when demonstrating this. But the idea is that they need to think about what other inputs are going to be there. What else do they need to think about when programming this artifact? What are the steps or the requisite steps of this algorithm in that middle process box, and how can they design that? And that's a really important step with this, because that's where the bulk of the complexity lies from the computational side of things. if you've got time and if the students need this additional support, you could even look at some examples of how to use some of the computational constructs within MakeCode. And this is creating a mock-up on the microbit itself. So the microbit has that 5x5 LED matrix, and this is an example of how to get the LED to sort of go up, across, down like that. And that's using the button press, so taking some input to start the algorithm, which links directly to the success criteria, and then using functions to sort of compartmentalize the different elements for it to go up and to go across and to come down and that sort of thing. And then you can just add them in then to a loop. So you're covering a whole array there of the computing curriculum by applying computational constructs efficiently. And there's obviously lots and lots of different ways of doing this. This is just one example. And the idea is that this makes them think about the right sorts of things, but they can't just directly copy it. It doesn't give them a solution. It just sort of teases them in the right direction in terms of the sorts of tools that they might want to do. And if students have not used MakeCode before, have not done any programming before, this will take a little bit of support. Usually they can work it out, and we've found when we've done this with schools that they do work it out quite quickly. It may not be the most efficient program, but that's not the issue. It's not about how fast it is, it's about whether it does the job or not. And again, that's one of the judging criteria of this as well, is to what extent is the code as elegant and as efficient as it can be. Okay, so that's part of this. The other part of this is testing it, because obviously the first time they will test this out, they may put this onto the microbit, then they put the microbit in the boat with all the elements, and then it may go in the completely wrong direction when they test it on the body of water, and so then they'll have to go back, unpick their algorithm and redesign it. They may have to change some of the elements on the motors and all that sort of stuff. And there's the physical side of that, like for example the size of the paddles, the weight of it, the buoyancy of the boat itself, and then there's also the how you program it. For example, how long the motors stay on for. Are they turning the motors on for the right amount of time to make it turn 90 degrees and that sort of thing. So there's lots and lots of testing that needs to go on as part of this, and that's why they need a full day to do this. It's not something that students will get right first time. So that's the programming bit. Now, looking at the sort of the physicality of this. Now, students may be, well, they should be familiar with what a boat is in terms of how it floats, but they need to consider the fact that this is powered by electronics, and electronics don't like water, and they need to figure out how to attach the motors to the paddles to make this thing go ahead. And because this artifact needs to be able to turn left and right, so it needs to be navigable, then you're going to have to use two of them. When students have designed this before, they put one like a single motor at the back, a bit like a speedboat, like an outboard motor, but that obviously can go forward well, but doesn't steer. And steering is a vital part of the challenge for this, and that's what adds in that complexity. So they will need to work out how to attach the motors to the hull of their boat, and also make sure that the paddles or the propellers will attach sufficiently to the motors themselves as well. And that is probably the hardest bit of this challenge, is having an understanding of some of the material science to make the paddles stick to the motor in a way that doesn't just shear off as soon as the motor turns. And this is why getting the motors with the right gear ratios is really important. Like 1 to 298, 296, I can't remember. That one is slow enough that that it will move forward slowly, and it won't just shear off at the first, depending on what material you use. When we did this without wood in the UK, they used like balsa wood. So it's quite thin, soft wood, and they use glue guns, and that worked quite well in terms of making the motors stick to them. If you've got access to other materials like cardboard, for example, that obviously can get wet. So think carefully about the materials that you provide to the students, because yes, it will be getting wet, and you need to try and get them to keep the motors dry and make sure that the motors can spin the paddles sufficiently. So hopefully that makes sense. But yeah, that typically is the bit that comes unstuck with students, because it's more of an engineering challenge than it is anything else. You can get packs from various suppliers which have the motor and then like a sort of a Lego clip that goes over the top, and you can screw that to like a bit of wood or a bit of cardboard or whatever. And then the servos tend to have, it's like a flat, it's like think of a round spindle with a flat section, and then you can stick the wood or the cardboard or whatever to that. So there's various ways of making this work, but something to consider. So in terms of preparing for the day, all of those elements I've just mentioned, it's worth thinking about when you're buying the making elements for this. You can either provide that for the learners and give them sort of a baseline set of kits like bits of cardboard, balsa wood, all that sort of thing, stuff to decorate it with. So if they're branding their product, then you need to give them things to do that. Kids love things like googly eyes and that sort of thing, and give them stuff like felt tips and whatnot. If you're using glue guns, obviously you need to consider the safety elements, because obviously glue guns get hot. You also need the consumables, such as the glue bits that go in the back. It's also useful to have spare batteries, because when you buy the microbit kits, they tend to come with AAA batteries, but if they've been sat in a warehouse for some time, those batteries may not work, so it's worth getting some spare ones. Also consider tools that you need. In this project, by default, you will need mini screwdrivers. Now, these can be purchased very, very cheaply. You can get sets of 100 for about £10. So these things can be got hold of relatively easily. The trickiest bit with the hardware for the organisers is probably the body of water. So not just because you need to get hold of a paddling pool, but you also need to fill it up safely. And if you're doing this on like the third floor of a building and there's electronics running under the floor, it's something to consider. So do think about where you're going to put that, how you're going to fill it up, and more importantly, how you're going to empty it. That can take some time if it's a relatively large paddling pool. So these are all the sort of little nitty-gritty bits that need considering and need setting up beforehand for these things to work properly. And there is a parts list which lists all of this stuff out with links to suppliers that we've already supplied, I believe. So you should be able to see that and get all of everything that you need. So this is a relatively fiddly project in terms of the electronics. So it's worth considering all of these things. So in terms of preparing for it, this is all the hardware that you need. As you can see, there's the basic microbit and the battery pack. They also need this thing called an automation bit, which is an additional control board with some pinouts for motors. You also need the header wires, and it's important to get lots of header wires because you need to have male and female, and some of the packs come with both female or a mixture of either. So it's important to have plenty so that they can connect all of these things up. And also with the motors, make sure that the motors have header shims on them so that you can connect the header wires directly to the motors, because some of them come with just a little tab with a little hole in it with the expectation that you solder them on, and that's really, really fiddly. And when the connections come loose when it's moving around, it just makes the entire experience a little bit awkward. So it's worth getting spending an extra couple of pence to make sure that the motors have those shims on it, and it just that's an issue that we experienced previously. They also need, they need at least one microbit per team, but if you're giving each student a microbit, that covers that sufficiently. Obviously, you need the battery pack, and you need the USB cable for their laptops. You can download the microbit hex files directly onto the microbit via the web, so you don't necessarily need to have local storage, but that's another option should you wish to do that. And it's to replicate the smart material. It's a good idea to have a sponge that they can then attach using tape or string or whatever. And then that is another sort of physical aspect that they need to consider when developing their boat drone, that it has to be able to drag this material around it as well. So that's something to consider in terms of the physical hardware. And the hardest bit is probably purchasing the hardware, but not necessarily setting it all up and using it. But if you do get a chance to try to have a go at this yourself, because this makes troubleshooting on the day much easier if you've actually built this thing. It doesn't take long to do if you put your mind to it, and it'll make you a much more effective deliverer of the project if you can do it yourself, because you'll trip over exactly the same sorts of things that your students do on the day. So this is a picture of the sort of finished product, and you can see there, look, you've got your motors and the board all plugged together. And students, if they've not played around with electronics before, it's worth pointing out some of these things. Like if you're using this specific automation bit board, they need to put the power 2 pins in the same hole, which seems kind of counterproductive, but that's how that particular board works. If you're using a different control board, there are several motor control boards available. Some of them have additional 3-volt outs, others don't. So depending on what board you're using, if you're using this one, then this solution works fairly well. And as you can see there on the motors there, as highlighted, it has the headers pre-soldered onto the motors, which makes everything a little bit easier, as I mentioned before. It's also worth explaining to students why you need a ground. Even though the voltage is very, very low, and it's only 3 volts, it's worth having that grounding thing in there, just the general knowledge of why you should be grounding these things for safety. So what else do you need to think about? So in terms of organising kit for the day, you'll need, it's a good idea to sort of purchase all that hardware, put it into like kits. It's a good idea to have it in like a bag or a box or something so that you can have one for each team. It's useful to have a sort of a space like a table or two tables where you can have all of those things with team numbers on there so the teams know where to go. You can get the students to bring additional making material if you want to. For example, you could say to them, bring your own decorations, and then they can colour it and put additional stuff on it if they wish to. But yeah, it's a good idea to have a good selection of these making materials, and that's the important thing to get right, because you need lots of it, and or at least a bare minimum for each team. And if because of the competitive element to this, it's a good idea to have the same set of kit for each student. So keep that consistent, and then it's fair. And as I've mentioned, some of these additional struggles already around attaching the motor to it, etc. Header wires coming loose is one of the biggest problems with this as well, because if the header wire comes loose from either the automation bit or on the motors, whilst the algorithm is running, it tends to derail things a little bit, and then it can act a little bit peculiar. So just explain to the students that they need to make sure that the header wires are secure, otherwise things may go slightly wrong. And being watertight is probably the most important one. I don't believe we sank any of them at the last one, but yes, microbits don't like being wet. Other things you need to consider is power. If you've got, like, for example, in a big room with lots of tables, each table will need a power supply for the laptops, because these will be used all day, and most laptops, won't last unplugged all day. And they obviously need a Wi-Fi extension as well. They'll need some room to build this sort of stuff. And if you're using things like glue guns and anything electronic, obviously that needs additional plugs as well. It's a good idea to have the making space and where the kids eat separate. Kids are messy. I'm sure we all are aware of that. So having separate spaces is a good idea. And also, if you're catering, if you are laying on food, then obviously do check the catering facilities that are available at the venue, because that's another complexity that you will need to navigate as part of this. So I've already mentioned parking and access and egress, but it's useful having some sort of emergency assembly point. Most facilities and buildings have this sort of thing, but it's worth covering this when you do the introduction for the day. Tell the students where to go if there's an emergency or if there's a fire alarm. Show them where the fire exits are. Have signage if it's not immediately obvious. It's also a good idea to signpost where the facilities are, like the toilets, and make sure that no other adults are going in there. Make sure that the laptops that you're using have accounts set up. It's a good idea to have like stickers on the laptops themselves with the username and password, or just have it completely open so there's no login at all. But that's just another thing to consider. And as I mentioned before, making sure that the firewall allows access to all the libraries that are required. So MakeCode is a fairly easy one, but GitHub, typically is blocked within schools. But if you're doing this somewhere else, just another thing to consider. It's also worth having, if there is a technician on site in the school, somebody who has access to the administration of the network, is to have them there at the beginning just to troubleshoot, because once it's working, it's fine. But the last thing you want is to start the competition and then the internet not work or something like that. So it's yes, make sure that's there. And if you are giving access to social media for the students, make sure that's unblocked as well, because that typically is blocked on school networks. So just bear that in mind. Also, safeguarding is a really important thing to consider with all of this. Nobody wants their kids to be at an event which is not carefully monitored, and making sure that every student is looked after and safe. It's a good idea to get parental consent forms. Schools typically will have this mechanism for this already in place. So parents either sign it at the beginning of the school year, or you can have a separate, distinct sheet to cover all of that. You may require that for insurance, for example. So it's a good idea to make sure that you are fully insured for the day. And as I already mentioned, media consent is useful. It's a good idea to have registers as well, so you have an idea of what schools are coming, who the students are, who the teachers are, so that you know when they come in, when they leave. And that's, if there is, for example, an emergency, it's a good thing to have access to. It's a good idea to have some sort of behaviour policy as well. Now, this can be relatively light touch, but if, for example, one of the students does have a meltdown, it's good to have a procedure in place for how the teacher, somewhere they can go that's quiet and out of the way, that the teacher can speak to them. This is obviously it's a rare thing, but it's just something to consider. And as I touched on before as well, it's really helpful to have toilet policies in place. Ideally, you want facilities for both boys and girls that are separate and no adults are in there. And if they are away from the main venue, have like the teachers escort them to the loos and the way outside, and then escort them back again, just to make sure that nobody gets lost along the way. And ideally, you want to make sure that there are no third parties have access to the students unsupervised at any point. It's fairly common sense with schools, but yes, you don't want anybody having access to students that shouldn't be doing so. Again, signage for accessing egress, I've already mentioned. Now, we have a mechanism in the UK called DBS, which is where, and there's a similar thing in the US as well, where volunteers that work with children are vetted by the police effectively, and if they have a criminal record, then they fail the DBS check. And most countries will have something like this, and it's worth making sure that all volunteers that are working with students have this in whatever jurisdiction that you're working in. I think the US, they have some, I think it's the CIA, I think they have it. You can apply and they do a criminal record check. So that's something to consider as well. Schools often require these sorts of things if you're going to be anywhere near their learners, so just bear that in mind. And risk assessment, that's really important. We have a template risk assessment that you can use, but it should be obviously updated and customized for whatever venue you are thinking about using. And this sort of stuff needs to be checked and updated just for liability reasons as much as anything else. And the insurance company may wish to see that as well, potentially. So it's something to think about when putting all this stuff together. And also a complexity for schools is, or two big complexities. One is the DBS checks or equivalent in the jurisdiction. It's travel, which is their problem really, but that can make events come unstuck. And risk assessments is another one. So if you can provide a risk assessment to the schools, that will make their lives easier. So here's a sort of a rough agenda for the day. It's a good day for them to sort of start arriving between 8:30 and 9, with traffic and just the general nature of wrangling children. There can be delays and teams often can turn up late. So have a sort of an arrival and registration thing, and then having an event start where you welcome everybody, explain what the structure of the day is, make sure you go through all the safeguarding stuff, where the toilets are, where the fire exits are, all that sort of your typical administration stuff, what to do in the case of an emergency. Run them through the context, explain it, answer any questions that any of the students might have. Spend time going through the success criteria, make sure that they understand what the success criteria is. And if you have audio-visual facilities, leave the success criteria visible all the time. So have them on the display on the projector or whatever, and so that they're always visible. And it's a good idea to have them printed out on each desk as well. They are on the design sheets, but it's just the more students see that, the better, because that's what they're being judged against. Then it's good to break up the day into sort of distinct building sessions. So the first one is like design and build, where you'll encourage them to spend the bulk of that time designing it. And if they are happy with the design, then they can start to build. Build in a little break where they have a chance to go and get refreshments, water, etc. And then have another session, then lunch, then the third session, and just making sure that in the third session they are considering testing, because the third session is the longest. And as part of that, they need to factor in when they're going to start to test it, because they can't all test it at the same time. You may have multiple paddling pools, for example, which is fine, but yeah, it may be a couple of minutes per team to test. So that does eat into time very, very quickly, especially if you've got lots and lots and lots of teams. So do bear that in mind, and make sure you leave enough time for the pitching. And you can do these two things at the same time. So you can have some judges going around and filling in the mark sheets and judging each of the team's projects, and then you can also have the teams doing their Dragon's Den presentation at the same time or separately if you've got the same amount of judges. But it's good to do them in tandem, because it can be quite time consuming. Even though the pitches are only 2 minutes, there's usually questions, then you have to get the kids in and out and all that sort of stuff. So yes, just think logistically about wrangling and herding kids. It can take time. And then give yourself a good bit of time at the end for the prize giving. It's worth wrapping this sort of stuff, reflecting on the day, explaining why this sort of thing is important, and then obviously awarding the prizes to the winners. And this doesn't necessarily need half an hour, but it's if you're getting, like, for example, the winners to talk about their project and why to get them to explain, redo their pitch, if you will, to the rest of the group. That's quite a nice thing for them to do as well. And then finishing typically at the end of the school day at 3 o'clock ish, and then moving on. So that's a sort of a general structure. Again, it's all malleable. You can do whatever suits you on the day, but that's it's that sort of approach works really well for us. So what else do you need to do? Prizes. So consider how much of your budget do you want to put towards prizes. This is coming from a tech company, so it shouldn't be too trivial. It's worth spending a reasonable amount of money on the prizes. You can have prizes for each of the different categories if you want to, or just one grand prize. The students are all getting a microbit as part of the day, so they're getting a prize anyway. But yes, don't be don't hold back on the prizes. It should be something that they really do earn, and typically you'll get a lot of students that go quite far with their product, and so it's the one that comes out on top is typically pretty good. So it's reward them for that. You might also want to get some guest speakers involved. If you, for example, if you're doing like a space themed project, you might want to get somebody from NASA or a space themed company to come and do a talk, and they may want to come and do it at the end during the prize giving, for example. So that might be a nice touch, but don't do like hour-long presentations to kids because they'll switch off and fall asleep. You may want to get some other third parties to come in and have stands on the day, more aimed at the teachers, so local exam boards, ed tech companies, or publishers that may want to try and sell stuff to the teachers or give away freebies, that sort of thing. And that's something it's an extra value add for the teachers that are coming along. They can all be done on stands. You might want to collaborate with other companies locally. There's lots and lots of very goodwill in the sort of the ed tech space, and from other tech companies, and they may want to come and sponsor the event. They may want to pay for the refreshments or the travel for the schools. That's always a big cost. You can get them to sponsor the merchandising, for example. There's lots of different ways that people can throw money at this from their CSR budgets if they wish to, without necessarily getting involved in the running of the day. And it's also a good idea to have some social media. So have a hashtag. Put that everywhere as well. Get kids to, if they're tweeting or doing TikToks or whatever, or anything on Instagram, use the same hashtags that we can monitor this and see the impact of it. You may also want to get in contact with local media companies. They will typically love this sort of thing. If there's kids doing interesting stuff with tech, that makes for a great photo opportunity. So if you've got contacts with the press and the media, then you obviously bring them in. You may want to do a press release, even if you want to go super serious with this sort of thing. It all depends on the scale and the size of the event you want to do. A lot of this stuff is a bit overkill if it's just a small event. If it's like less than 100 kids, it's relatively small. But if you're going bigger than that, then it's you may want to consider these sorts of things. And as I mentioned before, in terms of capturing the media, that makes some really, really good media assets for comms. There's tweeting about this sort of stuff, doing videos for it. We use this stuff throughout all of our marketing material, and it's really, really powerful stuff. So yeah, if you do get a chance to do that, do so. And that obviously takes a little bit of extra considering, because you have to get suppliers that are already vetted and all that sort of stuff. But it's something to consider. So on the day itself, it's so this is really talking about the introduction, which I've already touched on elements of this. So where to go, where the toilets are, where to go, what not to go, who to ask for help. It's a good idea to have some way of the volunteers being recognisable. And it might just be the fact that they're an adult, but it also you may have some sort of branded T-shirt or something. If this is like a Team Arm event, get them to wear a Team Arm T-shirt, something like that, and then they can be sort of going between the teams and interacting with them and helping the students where they may need it. It's also useful to make sure the judges are familiar with the judging criteria, because that's, if they've not seen that sort of thing before, it's worth them reading through it before they do it. And throughout the day as well, there's a temptation by some teachers to, because it's a competition, it's just to interfere a bit too much. And so if you can keep an eye on teachers not providing answers or helping students too much, that's a really good way to do it. And you can brief teachers beforehand as well about not interfering too much, and only support them when it's absolutely necessary, and ideally keep them away. But there is that safeguarding issue. They need to be within sight of their students. And you get the volunteers in particular to use active questioning, so open questioning. Why does this work? Talk me through this code, or the sorts of things that I explained before. And especially when they come unstuck or they run into a problem, use open questioning as a mechanism to get them to think about what they're doing, and without necessarily telling them the solution. And always refer back to the success criteria. I can't stress that enough. That's really important that they are thinking about that, and also going back and looking at their design sheets as well, because they may have the solution there in front of them, but when they've started to build it, it may have gone a little bit off piste, and so they need to refer back and maybe iterate on their designs as well. And so that's that. Now, preparing for the day for the participants, it's a good idea to get them to at least be aware of what their internal administration process is. So get them to look into what their process for organising travel is. I know in the UK, lots of schools struggle with setting up school trips, especially booking transport can be expensive for schools. So get them to plan well in advance who's going to be organising this, who's going to be filling the forms in, who's paying for what, and that sort of stuff. And again, making sure that you have access to these risk assessments and somebody that is competent and has an idea about risk assessments to fill this sort of stuff in, if that's required in your jurisdiction, of course. And again, as I mentioned before, gathering media consent and that sort of stuff. And also, if you want to get them to bring additional material, prompt the teachers to do that, because this all takes additional time and thinking about as well. Some schools like to prepare for this sort of thing. Now, whilst these tasks have been designed so that a student could access this project without ever having seen a microbit before, some schools may want to do a little bit of prior prep. And the idea is with that is to not to give the game away in terms of giving them the success criteria and the challenge ahead of the time. Just say that, you may want to say we'll be using automation bits, for example, and microbits, and having students at the very least understand that they have to code something in MakeCode and then download it to the microbit. And as long as they're happy doing that, then they're good to go. So, but yeah, don't preempt the problem too much with teachers that are doing this.